Well, do you have any questions before we get into the section?
No, I don't think so.
Okay.
I should warn you though, my internet has been um, dropping me. So for the last few days, I've been struggling with it. So I might get cut out of here
All right.
at some point during the class.
That's frustrating, isn't it?
Very frustrating.
I actually had to get a new computer in March when we went online because my computer was throttling the internet. Other computers were doing fine, but they didn't have the video chat and so on. So I actually had to get a new computer. Hopefully yours is just a temporary overload in your neighborhood or something.
Yeah, I think it is. I hope it is.
Well, let's go ahead and get started. If you do get cut out, we'll understand. And we'll have the recording. Hopefully you could watch that later if you need to.
Okay.
So yesterday we started into section 10.3 with hyperbolas. And so I thought it might be good if we continued that work and just practiced hyperbolas a bit more. And then we will get into 10.4, which is the section on nonlinear systems of equations and inequalities, which is building on our previous work with systems of equations. So it shouldn't be too hard for us. All right, so here we've got a problem where we're asked to find an equation of a hyperbola. And just as a reminder, our basic equation of a hyperbola will be, it'll be x or y. So I'm going to go ahead and put x minus h squared over a squared minus y minus k squared over b squared equals 1. That's kind of a general equation of a hyperbola. Sometimes this first one won't be x, it might be the y minus k here, or which would put the x minus h here. So those can swap. Everything else will stay just the way it is. But let's go ahead and plot these points so we can figure out whether it is x or y here on the left-hand side. So vertices are 0, negative 4, right there, and 0, 4, right there. Foci are 0, negative 6, and 0, 6. So this tells me, just because of the locations of the vertices and foci, that I have a horizontal transverse axis. The line that connects those 4 points is horizontal. And when that's the case, we know that I'm going to go ahead and cross out the y, k, x, and h because we know that the way I originally wrote it will be correct. When you have a horizontal transverse axis, then you get the x term first. And that's on our conic summary sheet. So we know that's the case. Now, I need to find the center. If you'll recall, the center is at HK. And it is exactly halfway between the vertices. So halfway between negative 4 and 4 is right here at 0. And it would be 0 in the y as well. So the center of this particular hyperbola is 0, 0. So that gives us our value for h and the value for k. Those will both be zeros. Now we need to figure out a and b. Based on what it says in our conic summary sheet, a is the distance from the center to each vertex. So we've got the center. The distance from there to a vertex is a. So now we know a is 4. So I can cross that out and put a 4 there. They tell me B is a point on the conjugate axis, that's the one that's perpendicular to the transverse axis through the center, but it is not a point on the hyperbola. And that's fine. But the reason I say that is fine is the next bullet point on our conic summary sheet says that C is the distance from the center to each focus. So from the center here over to the focus, that is our C value. And we are told in that box on the right side of the conic summary sheet for hyperbolas that C squared equals A squared plus B squared. This will allow me to find B. I know C is 6. A, we already figured, was 4. So now I can go ahead and square these. Subtract 16 from both sides. And now I know B squared. So I'm just gonna cross out that whole thing and replace that with 20. Rather than converting that to solve for B, which I don't really need it well, no, I do want B actually, so I can graph this thing. They don't tell me to graph it, but I'm going to. So that'd be the square root of 20, and recall that's plus or minus. And the square root of 20 is, because 20 is 4 times 5, and 4 has a square root, we've got plus or minus 2 root 5. So the B would be 2 root 5, and the square root of 5 is going to be about 2.2, I think. Let me quick double check just to be sure. Yep, 2.24. Multiply that by 2, and I get 4.47. So B is about equal to 4.5, just for graphing purposes. So I'll come up 4.5, put a line, come down 4.5, put a line, and recall that this connection through the vertex creates this little box that will help me in graphing. It goes through the vertices and it goes through the B. And if you'll recall, what we did is we said, well, that allows me to find the asymptotes. Oh, that didn't really connect through a whole bunch, did it? Oh, that was not a good one. Something like that, and the same thing over here. Extend it down a little bit. I think it's weird that that's fading off the way it is, but it might me. So my graph, recall that the foci are within the cups. So my graph will go from the vertex up and approach the asymptote, but not cross it, both up and down, and it'll have a second side over here. So that's the graph of this particular hyperbola. Just those two cup shapes. They actually asked for the equation. So let's go ahead and plug in what we know. We know that H is 0. We know that A is 4. We know that K is 0. We know that B squared is 20. So let me simplify this down. And that would be the equation of the hyperbola that had vertices and foci as given in the problem. And like I say, they didn't ask me to graph it. I just kind of like graphing these and wanted to use it as an example for how to do that. But it allowed me, by graphing the points, it lets me easily see if this has a horizontal transverse axis, meaning the two cups are going to open left and right, or a vertical transverse axis where the cups open up and down. And I know cup is not the technical mathematical term, but they look kind of like cups, and it's easier for me to understand and convey what I'm talking about. But now that I know it's horizontal, I can look at that part on the conic summary sheet and pay attention to just that, as well as the information over in the right column to help me find out what A, B, and C are and how those relate. So that's how we would solve a problem like this, where they just give us some points and ask us for the corresponding equation. Have you any questions about that? All right, let's try another one. This time, we're given the equation and we need to find the vertices, foci, and the equations of the asymptotes, and then graph it. So I'll bring this equation down here. Our hyperbola always is set equal to 1. So I'd better get this 1 over here. So I'll divide by 144. That'll leave me with a 1 over there on the right-hand side and give me the denominators. And it turns out that 9 times 16 is 144. So this simplifies to x squared over 16 minus y squared over 9 equals 1. Now, as a reminder, this first denominator is not always the largest one. It is in this case, but for a hyperbola, it's not always the largest. Just keep that in mind. All right, but the first one is always a squared. And the second one is always b squared. So there's nothing subtracted from from x, so that tells me h is 0. There's nothing subtracted from y, so that tells me k is 0. If a squared is 16, then a equals 4. If b squared is 9, then b equals 3. Knowing those and that c squared equals a squared plus b squared for a hyperbola, I can plug those in. I've already got a squared and b squared. Those are the two denominators. So I didn't actually have to square the 4 again and the 3 again, but I do need those for graphing purposes. 16 and 9 are 25, so C is 5. All right, so the center is HK. So that'll be 0, 0. The vertices, now as a reminder, I've got x squared positive. When x is the positive term, I have a horizontal transverse axis. And my conic summary sheet bears that out. And it tells me right there that the vertices, and I'm going to go ahead and write this down, are h plus or minus a, keep the k. And so that tells me in this case, h is 0, plus a plus 4 would be 4, keep the k. And then we also have h minus a, so 0 minus 4, keep the k. So those are our vertices. The foci, according to our conic summary sheet, are h plus or minus c, and keep the k. So h is 0 plus 5, keep the k. And then we've got h minus 5, keep the k. So now we've got center, vertices, and foci. Now something we haven't talked about yet is how to find the asymptotes. Now that is written right here on our formula sheet, our conic summary sheet. It says y minus k, and this is for the asymptotes of a hyperbola with a horizontal transverse axis. Y minus k equals plus or minus b over a times x minus h. And so we know, what do we know? We know k is 0, we know h is 0, we know b is 3, and we know a is 4. So we plugged in all of those values. So that tells me my asymptotes are y equals a positive 3/4 times x minus 0, and y equals a negative 3/4 times x minus 0. So those are the equations of our two asymptotes. Now we can go ahead and graph this. The center, let's change colors just for fun. The center is 0, 0. The vertices are 4, 0 and negative 4, 0. The foci are 5, 0 and negative 5, 0. A is 4, so that's why we came over 4 right and left. B is 3, so I can come up 3 and down 3. That will actually allow me to create my box. And recall, this box is really just to help with graphing, because the asymptote actually connects the corners of the box. And so if I were to start at the center, up 3 over 4, up another 3 over another 4. Come on, I wish that. So there's an asymptote. We can continue the same thing down the other direction. Let's see, it was up 3 over 4. So you can see that there's our asymptote. If I could draw a straight line, it would be great. And then we've got the other one. Going through here like that, or up 3 over another 4 like that. And so we could start at our vertex and approach the asymptote. It won't cross it. And we've got our hyperbola graph. And now we have found vertices, foci, and asymptotes, and then graphed it. So we have solved this particular problem as written. And you can see that those asymptotes are following y equals 3/4 x. That would have a, remember, plus 0. So the b is 0, the y-intercept is 0. Slope is 3/4, up 3 over 4, up 3 over another 4. So that's working just fine. And then we've got negative 3x, and I'm going to go ahead and write plus 0, though we don't usually, just to highlight that we have a y-intercept of 0, a slope of negative 3/4, so maybe up 3, run negative 4, and then up another 3, run another negative 4, takes you out there. You can see that those lines are indeed the appropriate asymptotes. So that's pretty much how we solve hyperbolas. We've solved now 3 of them. The one yesterday we had to complete the square a couple of times. So don't forget that. But today we looked at, well, what if we're given foci and vertices? And I reminded us that if we're given points, go ahead and graph those so you know the shape of this particular function. And then you can look at the right spot on the conic summary sheet to know how to access and use the formulas appropriately. And then we had this one where they gave us the equation, we just broke it down into pieces. Do you have any questions on hyperbolas? I'm going to do a slightly different exercise here next. Okay. So what I'm going to do now is I'm going to write out some equations, and we're going to talk about um, how to know what shape we've got there. So say we've got x minus 4 plus 4y equals y squared, or 3x squared plus 3y squared equals 75, or y squared equals 16 minus 4x squared, or x squared equals 4y squared plus 36. So we've got four equations here, and the question is, what types of graphs would they give us? Can you tell just by looking at what you see in the function? Looking at this first one, I've got an x term, and I'm looking at the term with the largest degree for each variable. So I've got an x term, and I've got a y squared. When I've got one squared term and one term that is not squared, that's a parabola. Just by looking at the function, we can see that. We've got an x raised to the first power and a y raised to the second power. And I know we've got this y raised to the first power here, but I could bring that over, complete the square, and I would have a y minus k squared over there. And that works out fine because our parabolas can look that way. But key is that the largest degree of x's is 1 and the largest degree of y's is 2. That gives us a parabola. And because y is squared, it is opening left or right, not up or down. And this one's probably opening to the right, but we would have to go ahead and do the math to prove that to ourselves. So I don't need this right now. Here, again, largest degree, I've got x squared and y squared. As soon as I have both of those squared, I know it is either a circle or an ellipse. Oh, no, I don't know that yet. But when I have both of those squared and they're added together, that's when I know it's a circle or an ellipse. So that is absolutely true. Now, how do I tell which one it is? And I do that by looking at the coefficients. The coefficient here is 3, and the coefficient here is 3. So if I were to divide both sides by 3, or divide both sides by 75 so that the right side equals 1, I would get the same denominators under x squared and y squared. I'm going to go ahead and divide by 3, and I get x squared plus y squared equals 25. That's a circle, not an ellipse, because I've got either the same denominator. If I were to divide both sides by 75, it would look like x squared over 25 plus y squared over 25 equals 1. So if you've got the same denominator in this, that makes it a circle, or which means you could multiply both sides by that denominator and end up with this equation so that you can quickly see r squared. So all of that together tells me that's a circle. Here I've got an x squared and I've got a y squared. This one's subtracted, but remember they're not on the same side. So let me get them on the same side by adding the 4x squared to both sides. And now I can see that I do have x squared and y squared on the same side. They are added together. So that circle or ellipse, they have different coefficients. So that's an ellipse. And I am going through this exercise for a reason. And we've talked about it almost every day for the last week or more. How to tell by looking at the formula of what we're talking about. But in your homework, I was just looking at it earlier today, it gives you a system of equations and asks you what the graph of that system would look like. Now, it gives you four things to choose from. And if you can recognize at a glance what type of figure it is, you can get that question ready or get it right really quickly. Because in one, they may give you a parabola and a line. The next one will be a circle and a line, then a hyperbola and a line, then an ellipse and a line. So really it's just recognizing, do I have a parabola, circle, ellipse, or hyperbola? And now you pretty well already know what's going to happen with this fourth one. Because as I get x squared and y squared on the same side, I'm going to have x squared minus 4y squared equals 36. I've got x squared, I've got y squared. They're on the same side, but they're subtracted. So that's a hyperbola. There's value in recognizing what the equation should give you, because you will feel much more comfortable graphing. You know what to look for. You know where on the conic summary sheet to look to get answers to help you figure things out. And so that's why I wanted to go through this and show how to tell the difference between those four types of equations and the shape of the conic section that goes with it. And it all comes down to how many squared terms you have. If you have multiple squared terms, get them on the same side. If they're added together, it's a circle or an ellipse. If they're subtracted, it's a hyperbola. The difference between the circle and ellipse is the coefficients to the squared terms. If they're identical, it's a circle. If they're different, it's an ellipse. And that's really, in a nutshell, how to tell at a glance which conic section you have from the equation. And that'll help you with, I think it's 4 homework problems in section 10.3. Oh, 10.4, I'm sorry, the start of 10.4. So let's jump over to 10.4 and see what we've got, what we're doing here. In this section, we are given a couple of equations, because we're talking now about nonlinear systems of equations and inequalities. So if I'm given x squared plus y squared equals 25, and 3x minus 4y equals 0, at a glance, I can see that that top one is a circle, because I've got x squared and y squared. They're added together and they have the same coefficients. And the bottom one is a line, because I've got x and y, nothing squared. So that makes that a line. Now, just kind of thinking about this for a second, remember systems of equations, we were finding out where two lines intersected. Well, now we're finding out where, well, specifically, a line and a circle intersect. So if I've got a circle, well, that's more of a skittle, and a line, how might they intersect? Well, the line could be up here. So there's no real intersection. The line could go right through the edge, where there's one point of intersection. It could go through here, where there are 2 points of intersection. So I could have no solution, I could have one solution, or I could have two solutions with a line and a circle. We need to know that. I mean, you actually have a homework problem that asks you that particular question. But knowing that, we can know what sorts of answers we expect to find. We could graph these two That's always an option. We have, let's see, x squared plus y squared, so the center is 0, with a radius of the square root of 25, which is 5. So there, 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 there. So let's see if I can draw a circle here. We already know I can't. Something like that. And then this one, that second one, I'm thinking, you know what? I like the slope-intercept form. So I'm going to move 4y to the other side and then divide by 4. So I get mx, well, plus b is 0. So again, we've got a line with a y-intercept of 0, a slope of 3/4, so up 3 over 4, up another 3 over another 4. There's part of the line, and then I could drop 3, run -4, drop another 3, run another -4, something like that. I keep holding down shift and it wants to give me sticky keys. So we can see that the line goes through there. I got to figure out why that's fading off. I'm struggling to draw a straight line. Regardless, we're okay. All right. So there are 2 points of intersection. How in the world do I find out where those are? Graphically, we've got a pretty good idea. But since I've already got this equation, the second one, solved in terms of y, why don't I do a little substitution and just take this and plug it in right there? That gives me x squared plus y squared equals 25. I just replaced the y with 3/4 x. We learned that substitution works really well as a way to solve a system of equations. And it turns out that that's going to be the method that we use most often in this section. Because elimination only works if you have like terms. And in order to get x squared and y squared on the denominator, we would have to square them, which would actually give us an xy term in the middle. Remember, foiling always gives you the outside-inside sum. And so then we would have an odd term that doesn't fit quite as well. So substitution will be your friend in here. So now we've got x squared plus 9/16 x squared equals 25. Well, to get common denominators, I'll multiply this by 16 over 16. Now I can add those. And when you add fractions, you add as long as you've got the same denominator, we just add numerators. So I've got 25/16 x squared equals 25. I'm going to now multiply both sides by the reciprocal of that fraction so that things cancel. So 25s will cancel, 16s will cancel, leaving me a 1. So I've got x squared. And over here, the 25s will cancel because recall this is over 1. And that'll equal 16. So I take the square root of both sides, and x equals plus or minus 4. Now that we know that, I can plug those in here. And y equals 3/4 of a positive 4. And y equals 3/4 of a negative 4. Well, as it turns out, the 4s are going to cancel. And I'm going to get y equals 3 when x is positive 4. And I'm going to get y equals negative 3 when, sorry, not y, when x is negative 4. And sure enough, I come over to 4, up 3. If I knew how to draw a circle, it would go through that point. -4, -3 again. If I knew how to draw a circle, it would go through that one. Boy, I did a terrible job of drawing a circle. But now we know the 2 points of intersection. They are 4, 3 and -4, negative 3. We could, if we wanted, go to Desmos and plot these. That's definitely an option. As a matter of fact, let me go ahead and do that. I think that might be of some value to us. I happen to have Desmos open. So we've got x squared plus y squared equals 25. There's our circle. And then we had 3x minus 4y equals 0. And there's our line. And now you can much more clearly see, hopefully this is being shared with you. Good. Just occurred to me that maybe it hadn't jumped over. But now we can see that this point is indeed 4, 3, because they draw circles way better than I do. And this point is also negative 4, negative 3. So we can see at a glance in this graphing software just where those points are. I suppose it's more than a glance. I actually held my cursor over it to give me the point. But there I've got those now. So it shows that the work we did in Photoshop was valid, except for my drawing. And so I suggest that you follow the procedure we did in Photoshop. Go ahead and do the substitution to solve for those points, because there will be times when, if we graphed it in Desmos, we would get an intersection that, well, maybe it's imaginary. Maybe that first option where they don't intersect occurs, and without the math, you won't know where the I is, what the value is, the coefficient for the I. It's also possible that Desmos might give you a decimal when what you need is a fraction, and the math itself will give you the fraction, and you won't have to rely on the decimal, because as you know, my math lab won't always accept a decimal. So we need to be careful with that. But I just wanted to see that we were actually getting the right answer, since my picture wasn't so good. All right. Let's take a look at another one. How about x plus y equals 5? And y equals 3 minus x squared. Okay, just looking at it, because this top one doesn't have any squared terms, I know it's a line. Second one has a y term and an x squared. When one is squared and not the other, that's a parabola. Now when it comes to graphing these, parabola could look like that. The line could be up here. Line could go through 1 point. Line could go through 2 points, just like a circle. We don't know which one this is, so let's go ahead and test a little bit. Let's do some substitution, perhaps. This second term is already solved for y, so we could take all of this and substitute it in for y in the first equation. We end up with x plus 3 minus x squared equals 5. Let's move everything over to the right, because I like a positive coefficient on the x squared term. So now we'll have a positive x squared. Subtracting x will leave a negative x, and subtracting 3 will be a 2. So now we've got a quadratic equation over here. Maybe I can factor that, though I'm starting to doubt it. X times x is x squared. 2 is prime, so the only options are 2 and 1. Because it's positive, they both get the sign of the middle one. Now, if I look at the inside-outside, I get minus 2x minus 1x, which is minus 3x, not minus 1. So it turns out that isn't the right way to factor it, but I followed all the rules. So I'm going to go to the quadratic formula instead. So a equals 1, b is negative 1, c is 2. So going to the quadratic formula, x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. So the opposite of b is 1 plus or minus the square root. Negative 1 squared is 1 minus 4 times 1 times 2 is 8 all over 2. We can see that we are going to get 1 plus or minus the square root of negative 7 all over 2. So we've got an I. I can actually just make that positive and bring the I out. We've got an imaginary set of intersections, which means it was that first one, something like that. So putting this into the a plus bi, we've got 1/2 plus root 7 over 2i, and we've got 1/2 minus root 7, that should be a 7, over 2i. Those are the two x values of the imaginary intersections. And now we could plug those in up here into the x to get the corresponding y values. And so we might do a, let me go ahead and hide the Cartesian coordinate system. Clearly we don't need it here. Y equals 3 minus 1/2 plus root 7 over 2i quantity squared. You can see this is getting ugly pretty quick, and yet it will still work out for us. Squaring this, you'd square the first one, which should be 1/4, and then we've got plus 2 times the first term times the second term. So 2 times 1/2 times root 7 over 2. Let's see what that looks like. 2 times 1/2 times root 7 over 2. We could cancel one of those, which leaves us with just root 7 over 2. We still have the I, though. And then we've got this term squared, which will give us 7/4 I squared. Looks crazy, doesn't it? But I squared is just a -1, so we can make that a negative. So now we've got 3 minus 1/4 minus 7/4 is a -6/4. I'm going to leave that way right now. We'll simplify it here in a second. Plus root 7 over 2i. So the negative, let me go ahead and distribute that negative through. Oh, we might as well simplify this now. That becomes 3/2. So 3 plus 3/2. Let's see, let's change that 3 to 6/2 so we get a common denominator. And 6/2 plus 3/2 is 9/2. You've got minus root 7 over 2i. So that's the y we get with this first x value. So the point of intersection, you get a different color here. We've got the x, half plus root 7 over 2i, with the corresponding y value of 9/2 minus root 7 over 2i. That is one imaginary point of intersection. Then we would plug in this x value in here, square it, and really the only thing that's going to do is make this negative, which makes that positive. So that second point would be 1/2 minus root 7 over 2i, and 9/2 plus root 7 over 2i. I'm not going to take the time to do that math because we only have 5 minutes left, But I did want you to see that sometimes we will get two things that don't actually intersect, and we end up with I terms, but we follow the same procedures to give us the solution. So that will work out pretty well for us. Granted, that's some extra math, and most of your work will not have that much extra math. I just wanted to show you a tougher problem than you're likely to run against so that you will know how to do it if you have to. Some other things to consider, maybe we'll have a hyperbola, something like that, and an ellipse. And the ellipse could be up here, again, imaginary. It could be, that's supposed to cross at one point. It could cross at 2 points. Ooh, terrible ellipse. It could cross at 4 points. For that matter, let me grab a different color. It could cross at 3 points. I didn't really grab another color. But you can see an ellipse and a hyperbola can cross at quite a few different situations. It could have 0 points, 1, 2, 3, or 4, but no more than that. And again, we already know how to evaluate whether we have an ellipse, a circle, a hyperbola, or a parabola. So that will give you a sense of what to look forward to. I did want to solve this equation, this problem. I thought this would be a good one because it's an application problem, and sometimes we can get a little anxious about those. So we've got a recreational building. An architect wants to lay out a rectangular piece of land. We know about rectangles. We've been working with those since probably kindergarten to recognize them anyway, but the math is new. Okay, rectangular piece of land. It has a perimeter of 204 meters. Recall, perimeter is the distance around outside. I'm going to go ahead and label this width and this length. And so if we add all of those together, well, this would be a width too, and that would be a length. We would have 2W plus 2L would be our perimeter. The area, they tell me, is 2565 square meters. Well, we get area of a rectangle is just length times width. So now we have two equations with two unknowns. We have a system of equations. They're nonlinear though, because here we're multiplying length times width and here we're adding length times width. So to solve this, maybe I'll take this second one and solve for L. 2565 divided by W. And now I could substitute that in up here. So now my problem is 204 equals 2W plus twice the length. So I've got to somehow solve this. Let me go ahead and multiply the 2 through. So we've got 2W plus, doubling that would be 5130 over W. Fractions make a lot of us anxious. Let's go ahead and multiply everything by the common denominator. So really I'm distributing that W through to all three terms. So now I've got 204W equals 2W squared plus 5130. I can go ahead and bring that 204W over so it looks like a quadratic we like. Those are some big numbers. I'm going to divide everything by 2 just to make it easier to deal with. So I've got 0 equals W squared minus 102W plus 2565. I'm not even going to try to factor that, though maybe we probably can. I'm going to go straight to the quadratic formula. So W equals the opposite of B plus or minus the square root of B squared minus 4 times A times C all over 2 times A. So let's take a quick look. What is 102 squared? And I'm saying quick because we are out of time. That's 10,404. 4 times 2565 is 10,260. And 10,404 minus 10,260 is 144. That's a nice square that we're familiar with. So we've got 102 plus or minus the square root of 144 over 2. So 102 plus or minus 12 over 2. That gives us two options. We've got the plus option and the minus option. 102 plus 12 divided by 2 is 114 divided by 2, that's 57. 102 minus 12 over 2 is 90 over 2, that's 45. And then we could plug each of those into this one to get length, and it turns out you get 45 if you plug in 57, and you get 57 if you plug in 45. And in English, we tend to say that the shorter side of a rectangle is the smaller number. So that will be our 45. The longer side is the larger number, or 57. So those are the dimensions of the land that has a perimeter of 204 and an area of 2565. And we did that with a system of equations. We knew how to calculate the perimeter of a rectangle. That was twice the width plus twice the length. We knew how to get the area, length times width. And so we just plugged that in and then solved it as if it were a system of equations, rather than worrying about what each of those variables represented right now. What mattered is that we wanted to solve what one of them was and plug it in and get the other one, so that then we could go back and say, well, what does that mean in this real world application? And we were able to solve it. And we are out of time. Have you got any questions on this at all? We'll finish section 10.4 tomorrow, where we're talking about inequalities. As you can imagine, it's these shapes, but we're going to be shading portions of it. And then we'll also do section 11.7, the binomial theorem, which is outside of conic sections, it's algebra. And so it'll be back to something you're a little used to, but it is a little weird too. All right, not seeing any questions, let's go ahead and call it a night, and I will see you tomorrow.
Thank you. Have a good one.
You're welcome. Thank you. Have a good night.